In section 7.1 we're going to be looking at the derivative of f of x equals b to the x and the natural number e. Usually when we look at functions we look at x as our base and then a numerical value or like x squared for our exponent, but now we're kind of reversing that. The base can be any number here that's positive. It can't be 1, but we'll look at those rules in a second. And the exponent is some expression involving x. So we're going to be looking at exponential functions. Exponential functions are used in a lot of different areas. Exponential functions can be used for carbon-14 dating, radioactive decay, life insurance, setting premiums because it's based on population growth, and also company pensions based on interest rate and population growth, people paying into the pension field. So again, exponential functions are used in a lot of different ways. An exponential function is a function that is of the form f of x equals b to the x, like we said before. And then we need to add to that where the base, and base is your b value here, is greater than 0, it's positive, and the base, b, cannot equal 1. So it could be a fraction, a proper fraction like 2/3, 1/2. It could be anything larger than 1 as well. But why can't it be 1? Well, let's go ahead and look at that real quick. Let's look at the case when b equals 1, and we'll see pretty quickly why it's not of much interest. So here, if we have f of x equals 1 to the x, we realize that 1 to the x is just a constant function. And if we were to graph that constant function, f of x equals 1, which is y equal 1, this line right here, we can see that that's not exponential anything. That's just a nice little line. So when the case b equals 1, it's not exponential. And it's not very interesting to look at either. So when b equals 1, it's not exponential, so that's the one case that won't work here. The next thing we want to look at are properties of exponential functions. Many of these properties of exponential functions you are already familiar with because you're familiar with the concept of an exponential function. But exponential functions are always positive. They're always above the x-axis, as long as of course there's no transformation taking place or anything like that. So they're always positive. They never are 0. They never cross the x-axis. Another way to say that is b to the x, our exponential function b to the x, is greater than 0 for all x. Now of course realizing that b cannot be equal to 1 as well. The graph will always be above the x-axis. That's an important thing to keep in mind when we're looking at the curve sketch. If my base of my exponential function is greater than 1, of course it can't be equal to 1, then my exponential function f of x equals b to the x is increasing. We have an increasing graph, and we'll show that here in a moment what that looks like graphically. Let's not do 3 here. If b is between 0 and 1, and of course I do not have 1 in either one of these cases, my exponential function f of x equals b to the x is decreasing. So if it's a proper fraction, my base is a proper fraction, it's decreasing. And the third characteristic that we want to look at is the range. And again, we'll see this graphically in just a second, but the range goes from 0 to infinity. And of course, in terms of y in interval notation, this would be between 0 and infinity for y. Notice we don't bracket 0, and of course we never bracket infinity here. Let's go ahead and look at a couple graphs there that accentuate these properties of exponential functions. So graphically, let's go ahead and look at f of x equals 3 to the x, and then also let's look at the graph of f of x equals 1/3 to the x. And it's quantity 1/3 to the x. And we're going to rewrite that one just a little bit too, but for now we'll just go ahead and look at this first one. F of x equals 3 to the x. Now if we plot some points here, this nice little hinge point shows up. If we plug x equals 0 in, 3 to the 0 is 1, so this is this nice point. And of course if I plug in 1, I get a 3 back out. If I plug in a 2, I get a 9 back out, and I have this exponential growth pattern. Now if you look over in this direction, if I have, let's say, 3 to the negative 1, 3 to the negative 1, if I plug that in, is going to be 1/3. So that's why I end up in the below area here. So what are some characteristics of this graph of f of x equals 3 to the x? Well, first of all, it's increasing. It's continuous. It has positive concavity. So those are all interesting characteristics. It has a horizontal asymptote as well. It has a horizontal asymptote at y equals 0. Now, if we were to try and find this horizontal asymptote using our techniques from Calc 1, we'd run into a problem. We need to use something called L'Hopital's rule to actually find this. But we'll learn that here pretty soon. So here's my horizontal asymptote. It never crosses the x-axis. And let's see what else. I also have some limits that I can look at here. The limit as x approaches 0 of this function is 1. The limit as x approaches infinity of this function is infinity. And the limit as x approaches negative infinity of this function is equal to 0. So those are some interesting characteristics of f of x equals 3 to the x. Now this would be a curve sketch of any type of graph where my base right here is more than 1. And now the larger the base, like 10, 20, 30, 100, the steeper this curve would come in toward the y-axis. Okay, let's go over here and look at the graph of f of x equals 1/3 to the x now. If we look at this graph, it might also be a little bit easier to look at this function in a little bit different sense. This is the same as 3 to the negative x. Okay, so when we look at it as 3 to the negative x, I see that negative exponent, and that kind of gives me an indication that I have, instead of exponential growth, I'll have this exponential decay. So I'll plug in that same hinge point. 0 for x gives me 1 out for my function, and I have this nice curve sketch for 3 to the negative x. Now this would be true for any base between 0 and 1. Let's go ahead and look at some characteristics of this function as well. This function is not increasing, it is decreasing. It is continuous, as was the last one. It also has positive concavity. It also has a horizontal asymptote, and I'll abbreviate that HA, at y equals 0. So let's go ahead and plug that in, or show what that looks like on the graph. Okay, and I also have some limits that I can look at here. So the limit, kind of split this off here, the limit as x approaches 0 of 1/3 to the x is 1. The limit as x approaches infinity of 1/3 to the x is equal to 0. It's going toward the x-axis. I'm going to sneak one more in here. The limit as x approaches negative infinity of 1/3 to the x is equal to positive infinity. So sorry I squeezed all those in there. Should be able to get those down. So those are all some interesting graphs, and you should be able to graph an exponential function and talk about the characteristics of these. One thing to note is an exponential function increases very, very rapidly. So if you were to graph x squared and 3 to the x on the same curve, they might look very similar in terms of their rate of increase. But if you were to graph x squared and let's say 10 to the x, 10 to the x is increasing very, very rapidly. The next thing we want to look at are the laws of exponents. These will be review from you from algebra, but they're definitely worth reviewing one more time. So the laws of exponents. We've already kind of looked at one of these. If I have a base to a 0 power, I get 1 back. Now we can't say anything to the 0 power is 1, because when we start talking about some different types of limits, we know that if we get a limit of 1 to the infinity, that is indeterminate form. So a constant to a 0 power is 1. We also have multiplying like bases. If you multiply like bases, you add the exponents. If you divide like bases, you subtract the exponents. And of course we know about reciprocating as well. b to the negative x is equal to 1 over b to the x. If we raise a power to a power, b to the x quantity to the y, you multiply the powers. And this one is not really a law, it's just kind of a remembering how to rewrite this. If I have b to the 1 over n, that means I have the nth root of b. So we can use all of these laws of exponents to rewrite and solve equations. And a lot of times we like to rewrite and simplify before we do any calculus. So this will come in handy. So let's go ahead and look at some examples. First of all, this is kind of a nice basic algebra example. Let's simplify this expression. First of all, it doesn't look like there's anything that we can simplify because I don't have any like terms. One of the first things I'd like to remind you is here, when we have this value, remember you don't take 3 times 4 to get 12 to the 1/4. The 1/4 only goes to the base of 4. But we can rewrite this quite a bit. So let's go ahead and look at that. 4 to the 1/4, if I think backward, 1/4 comes from multiplying 1/2 times 1/2, so I can rewrite that. And then also I can think about rewriting over here by flipping that exponent into the denominator. This value right here is the square root of 4 then. The square root of 4 is 2, and this first expression simplifies to 3 root 2. The second expression needs a little bit more work. When I rewrite this one, 3/2 is the same as 1 plus 1/2. Well, thinking backward if you'd like, remember when you multiply like bases you add exponents. So here I get 2 times the square root of 2. Now some of this is looking a little bit familiar. Maybe I can combine something soon. So minus 12 over 2 root 2. And of course 2 goes into 12 6 times. And let's go ahead and rationalize this denominator while we're here. So I end up with 3 root 2, okay, minus 6 root 2 from here over square root, or sorry, not square root of 2, but 2. Root 2 times root 2 is 2. Canceling one more time, I end up with 3 root 2 minus 3 root 2, which of course is 0. So that's just a very complicated way of saying 0.